Hello everyone, myself Sudipto. I have created a three-part video series about single phase inverter a few days back. Many of you asked me via my DM that show the gate pulses of the IGBTs of 4 IGBTs, and you wanted to know or you wanted to ask me to show the gate pulses and gate pulses of the inverter output as well, how sinusoidal it gets. So today in this video I will break down all the gate pulses via this oscilloscope and show you corresponding pulses or corresponding waveforms of individual points. So without wasting time, let's start the video. So in my last video series I told you about all the structure and how it works and how the gate pulse is generated. So here you can see I have connected my main DDC battery. This is a LiPo battery for demonstration purpose, and this is the DC-DC boost converter. These four are the 4 IGBTs with their corresponding gate drivers, and this is actually the gate signal generator board, and this is the step-up transformer, and this is a simple load. Okay, so now I have connected the system and didn't turn on the gate driver. So let me turn on the gate driver. So here you can see I have turned the gate drivers on. So the gate driver are on, and the signal generator are also on. That means the signal is generated. So I have connected these probes, or here you can see these probes and the ground to my ground, and these are the oscilloscope probes. So let me show the first IGBT gate pulse to you. So let me put the gate pulse section here. So in the oscilloscope, so let me take my hand here, and from in the oscilloscope you can see this is actually the gate pulses. And let me dive another let me use another of my probes. So come here, so let me connect another probe in another channel. So you could see that I have connected 2 probes in 2 channel. Okay, and these are the gate pulses. Okay, so here you can see these are the gate pulses from 2 individual legs. And just let me zoom it furthermore. So this is actually quite clear. The gate pulse is being changed, and here you can see this is the gate pulse, and this gate pulse is varying sinusoidally. So let me stop it. So here you can see this gate pulse is varying. So this is the starting of the sine, and the sine is flowing like this and this and this. Let me put the gate pulse here, and you could easily see this is actually a sine representation. So here you can see the sine is flowing like this. Okay, so sine is starting here, sine is starting here, and sine is flowing like this. So this will be not here, so this pulse will be corresponding downward to this one. Okay, and this is the sine representation. Sine will flow like this and this and this. Okay, so this second pulse is responsible for the negative half cycle of the sine wave, and the upper one, or the upper switch, is responsible for positive half cycle. Here you can see this is the corresponding two corresponding signal of the gate. And one interesting fact is that from the oscilloscope measurement you could easily see the peak to peak voltage, peak to peak DC voltage of channel 1 is almost 5 volt. So what that mean? That mean is the signal of this wave is 5 volt, and this I told you in the theoretical video, this is actually the low voltage signal. So let me show the gate driver voltage, or the gate driver output voltage, or what the gate driver is outputting. So here you can see I am connecting the wire to the ground of the gate driver, and the output to the gate driver output. So let's show the oscilloscope. Show on the oscilloscope, right? You could see you could easily see this is the output voltage of the gate driver. Okay, and one interesting fact to notice that the peak to peak voltage is almost 10 volt. Okay, peak to peak voltage is almost 10 volt. That means this pulse is of 10 volt peak. So now we are boosting the 5 volt peak to 10 volt peak via the gate driver circuit. Okay, so each of the gate driver is doing the same thing. The each individual gate driver is boosting the input 5 volt low logic voltage to corresponding 12 volt or 10 volt IGBT gate voltage. Okay, I'm back again with some simple modification in my circuit. So basically here you can see I have removed the transformer wire from the circuit. So here is the transformer wire. So I have removed the transformer wire. In my theoretical explanation video, I told you that this portion of the circuit is generating the sinusoidal from the DC bus voltage. So this portion, as for that reason, this portion is known as the inverter section. So what I have done is like I have removed the step up transformer and connected the load, or connected the simple load. Here you can see this is a ceramic load, and this is RL load in nature. I have connected this load corresponding to this in inverter circuit. So this point and this point is the output of the inverter. So I have connected the load with this, and I have removed the step up transformer so that I could show you how the unfiltered, or how the step up version of unfiltered voltage looks like. So let me turn on the power. So you can see I have turned on the power, and I have connected one probe here and another probe like here. So let me show the oscilloscope. So here you can see, and nothing is showing up in the oscilloscope because I didn't have turned the DC supply yet. So let's turn on DC supply. So here you can see I have turned the DC supply on, and this is the corresponding AC voltage. Corresponding AC voltage means that this voltage is generating from the inverter, and it's SPWM, or sinusoidal in nature. You could see this is a simple fundamental period of a sine wave, and let me zoom it a little bit. That's why you could see it more clearly. So let me show you a single shot. Here you can see, and this is a single sinusoidal pulse, and the pulse is varying sinusoidally. So this is the unfiltered pulse, unfiltered SAC waveform from the inverter section. Okay, so let me show the transformed version or step up version of the AC voltage. Hello everyone, I'm back again with the simple modification in circuit. I have connected the transformer to my inverter. Here you can see no loose wire is connected, or no loose wire is found, and the transformer is connected directly to the inverter. So let me show the AC filtered output, or the how the sinusoidal waveform looks like. So here you can see, let me turn on the gate driver supply on. So here you can see I have turned the gate driver supply on, and let me insert my oscilloscope probe into the AC cord. Here you can see I have inserted one probe, and this is the another probe I have inserted here. So let me show it to in the oscilloscope. Here you can see no waveform is shown here because I didn't turn on the DC bus voltage. So let me turn on the DC bus voltage, and here you can see the waveform is not sinusoidal because I didn't have turned this supply on. So this is the switch for this supply. So here you can see I have turned the sinusoidal supply on, and the light is like brightness, it's lighting in full brightness, and the corresponding output voltage or AC voltage, RMS voltage, is 163 volt. And let me show the waveform. So here you can see, let me scale the waveform a little bit. So here I have scaled down the waveform. So here you can see, and this is the corresponding SAC voltage. Here you can see the voltage waveform is not looks like pure sinusoidal because I haven't tuned the value of my filter bank, and you could easily see the RMS voltage is 116. Okay, the RMS voltage is 116, and what's our meter is telling us the RMS voltage is 115. So it's clear that it's quite good. And if we increase that DC link voltage, here you can see this is the DC link voltage potentiometer. I have already shown it in my hardware demonstration video how this is affecting the inverter voltage. So let me show it closely to you. So I am increasing the DC bus voltage, and you could see the corresponding AC voltage is also increasing. Here you can see it's now currently 135 volt, and let me increase a little bit more. So here you can see it's already 150 volt, and thus by increasing the DC bus voltage or DC supply voltage, you could easily max the AC waveform. And here you can see it's not sinusoidal, but we could call it sinusoidal. By tuning the value of the filter, we could easily get the sinusoidal output voltage. So that's all for this video. Thank you everyone for your awesome feedback, and if you want to know more and detailed analysis and total harmonic distortion analysis and other analysis, let me know in my DMs, or feel free to comment in the videos down section, so that I could make another video of it. So thank you everyone for joining me in this video.